Common emitter configuration. The emitter is both common to both base and emitter output collector. Okay, we did common base configuration. This is common emitter. Like I told you, you have to go by the name. Common emitter means emitter terminal, which is this terminal, is going to be connected to the ground. Okay, and it's going to be common to the base and also to the collector. Okay, how would you put it in a schematic? Well, it's going to look something like this. Okay, if I ask you if this is a PNP transistor or NPN transistor, what is the direction of this arrow? It's pointing downward, correct? Pointing downward. Therefore, this base over here, is it P-type or N-type? This base over here, is it P-type or N-type?
P-type.
P-type, because current always flows from positive to negative terminal. And if this is positive, this is negative, then surely this terminal, which is collector, is going to be N. So this is a NPN transistor. And if you notice, this is also NPN over here. Okay. All right. The input is on the base. This is your base right here. This right here, this is your base, right? On the left, this is your base, and output is the collector. This is your output. So similarly, the common emitter characteristics, if you look at the input side over here, the input side, this is your input side and this is your output side. So the input side current is IB, and then voltage is VBE, correct? VBE. You got base here and you got emitter. So this is VBE. So notice you got input characteristic VBE versus IB. Okay, so these are the input characteristics. Again, these graphs will be given in the data sheet. Okay, you don't have to confuse like how the hell we got this here. Okay, and similarly, this is the output characteristics. Sometimes they are written as collector characteristics because remember, collector is always your output. You look at over here. Sorry, okay, where did I go? Collector is the output here. Yeah, as I mentioned over here, collector is the output. So VCE. And then collector current is the output current is the collector current. So you say VCE here, and then the IC, that collector current, and there's a graph. And then these lines that you see here, folks, these lines over here, again, these will be in the data sheet. These represent base current. Similarly, these three lines that you see over here, these are VCE, that's the output voltage. So we got common emitter. Let's look at common emitter amplifier currents. We all know this equation. We are familiar with it. So IC equals to alpha IE. How do we get to this point? Okay, let me just make a block diagram of a transistor. This is your emitter terminal on the left. This is your base terminal here in the middle, and this is your collector terminal on the very right. So say you have, this is going to be, let me change the color. This is going to be IE, right? This is going to be IB, and this is going to be IC. Okay, so if you have n number of electrons here, okay, you have n number of electrons. And then over here, the number of electrons will be 1 minus alpha times n. And then here, the number of electrons will be alpha times, and we know alpha is a ratio of what? Is a ratio of IC over I. Also, you can also find out how did we get this equation over here. So alpha was equals to IC over IE. I can rearrange this equation such that it looks like IC equals to alpha IE, correct? Okay, and that's what it is. If you have n number of electrons here, the number of electrons here are 1 minus alpha times n, then this is alpha n, correct? Alpha is what? N is what? N is the number of electrons, and number of electrons here in the emitter is basically IE, okay? So if alpha n, if I replaced n with alpha IE, that is what the IC is, right? That is what the IC is, and that's how we get over here. Also, remember, folks, I think that I told you guys too. So say there are 100 electrons here in the n-type region, okay? There will be roughly 2 to 5 of them will be here, and then 95 to 98 of them will be collected at the IC. Okay, so that's how the contribution of these. So you have IE 100 electrons, IC will be say if 95, then IB will be 5. Okay, so that's how the we get this equation, and that's how the, if you want to put it into a numeric number. Okay, all right. Then we have IC, which is basically this collector current over here, right? This collector current. It's actually a sum of alpha IE plus ICVO. Like I was saying earlier, that you will have some minority carriers over here, which will be plus here. And also you will have some minority carriers over here in the base, and those will be negative, right? So these plus and these negative, they will be attractive towards each other, okay? They will be attractive towards each other, okay? This current is going to flow in the reverse direction, and that's what we refer to as the ICVO, okay? It's sometimes also referred to as leakage current. Again, it's going to be very, very small, and in some books they'll call it as a minority collector current. So it's usually very small. It can be ignored except in high power transistor and in high temperature environments. So if when IB is 0 microamps, the transistor is in cutoff region, right? The transistor is in cutoff region, but there is some minority current flowing called ICEO, which will be equal to this right here. Again, this happens only when the transistor is operating in a cutoff region. This ICO is going to be, again, a very small number. Beta represents the amplification factor. When we were doing op-amp, we had the gain here, correct? We were looking at the gain, okay? And if gain was, say, 1,000, we would know that it will basically amplify the input signal by 1,000 times. That the amplification factor in transistor, when we do analysis, is replaced by beta, okay? It's the amplification factor of a transistor. Beta is sometimes referred to as H and then FE in the subscript. Same thing. Most books will have beta here. A term used in transistor modeling calculations. Okay, so in a DC mode, BDC is basically equals to IC over IB. Very important equation. We're gonna use it a lot of times today and also Tuesday. In AC mode, it's basically change in collector current over change in the base current. Now, remember, this collector current is the output current, right? Collector current is the output current, and then IB is the base current, which is the input current. Okay, all right. So how do you calculate beta? Just looking at a graph. If I give you something like this, okay, how would you calculate beta? Beta AC, we know, is a change in the collector current. So say this is the Q point, okay? I'm gonna zoom in a little. So this is the Q point, okay? All right, so you look at the operating point above that, which is over here. You have to make sure whatever this line is, okay? And then you look at the line which is right below the Q point, okay? And then you draw the straight line like this, okay? And you draw a straight line like this, okay? And you note this value. Looks like it's 3 something, so it's 3.2 milliamp. And you note this value over here, which is 2 point something, so it's 2.2 milliamp. Okay. Similarly, you draw the lines vertically as well. You look at for the base current values. So for in this case, the base value is 30 microamps. So you get 30 microamps here. And then for this point, the base current is 20 microamps. So you get 20 microamps. So you do the math and you get a beta of 100. Pretty simple, basic stuff. These characteristics are extremely important. You cannot analyze any transistor without having this characteristic stable, okay? And if you look at it, if you draw a straight line like this gets you a VCE, and VCE, I told you, is the output voltage, okay? This is the output voltage. If you were going to do calculate the beta DC, is just simple IC. So if I can just delete that, you don't have to do this drawing the lines in that case. You only look for these values here. So this was the Q point, right? This was the Q point given in the question. So you just draw a straight line like this. So it looks like 2.5 something. So it was 2.7 actually. And then this line is basically 25 microamps. 25 microamps. So you get 25 microamps. So you do the math and you get 108. There's a slight variation if you notice. You got 100 here and you got 108. But that's something that you would expect. Okay, all right. Relationship between amplification factors beta and alpha. Alpha is going to be equals to beta over beta plus 1, and then beta equals to alpha minus 1. It's important to remember that also because we might need that. Some places we already learned IC equals to beta times IB. How did we get here? This equation, how did we get here? Well, we know that IE equals to IB plus IC, correct? IB, I just write it down as it is. IC is beta times IB. So I get beta times IB. And then here, if I take IB common, then I get beta plus 1, right? And that is IE, right? And if you look at this equation right here, is actually similar to this. So that's how they get here.